Hey, welcome to another coding session with Bangalang. Last session we set all this up, a whole bunch of OpenGL code that we're calling now, and we've got a triangle rendering, which is super awesome. And then I said the next thing I want to get onto is threading, which is true. I do want to get onto it. The next thing I realized that is needed for that is we need to be able to have some kind of like a function pointer or a procedure pointer. We need to be able to pass procedures around like they're variables. So then I can have like something like, you know, I don't know, start thread, and then I can pass in, you know, some procedure. That's kind of the idea. I did have a bit of a play with that. It's not an easy thing to do. And actually one of the things that was really tripping me up is our assembly. We did some work a while back to optimize it. And in some places it looks really good. You know, like this is declaring a bunch of, well, I guess we can't call them constants. They're not constants, but these declarations. So these look really good, you know, it's like we allocate some space on the stack by moving the stack pointer, and then we put our number on the top of the stack. So that looks really good. Here's something a little more complex where we're declaring, it looks like a pointer maybe. I think this is the null pointer down here, yes. We don't have a way of just specifying null yet. That's actually one of the things I'm thinking to do. But so this is basically allocating a pointer, 8 bytes, and then it's putting 0, it's just filling it with zeros, 0 initializing. So that looks good. I mean, this could potentially be done just with a single line instead of this because it's an 8-byte thing. Let's see. But look at this, you know, we've got deallocate 0 bytes. That's pointless. Wait a minute, let me, oh yeah, we did, okay. Just making sure we were running the right thing. So, because this actually looks surprisingly good. Oh no, it's keeping on going. That's all of this. All of this to call glfw create window. See, this is a bit much. I mean, come on. We've got 1, 2 allocations, then a deallocation, the deallocation. These look good. I think this is the string. Actually, that there is passing the string in to the procedure, passing in a C string. And it should be really easy, you know, I mean, it should be basically that, I want to say. I feel like that would do the job, you know, it'd be so much more concise. So I have a list of things that I just want to tidy up our assembly, because as it is at the moment, it's so hard to see what's gone wrong because there's such a big mess of stuff. So I have a list of things that I just want to tidy up. And there's also kind of a couple of language features that I want to have a go at as well. Like I want to have, like I alluded to this null pointer, I want to be able to just go nil like that. So I'll implement that. And then also it's a bit hacky that we have this. I think I want to do something like hash boundless, and that'll give us a pointer to I8, but it will have no bounds checking. So it could be any number of I8s. Yeah, I think I would like to do that because I think, so it's kind of like a C pointer, you know. Everything, I think kind of the idea in my language is that everything should be bounds checked. So, so this is just a way to override that. And the only way the only reason you should really want to do that is when you're interacting with C, and because C doesn't have that feature, we kind of need to have some sort of interoperability without this hacky 1 million. Okay, anyway, that's enough chatting. Let's actually implement some of this stuff. So here's my list. Remove allocations from string C string. So this is where I was talking about, this, I think it is, yeah, I think it's like this is our C string. Let's see if we can reduce that. And especially with C string, I realized, I just copied, where are we, primary. I kind of just copied, because here's our string, and then I copied that to make the C string code. But really, we don't need to do any of this stuff. We're allocating some space when the C string can fit inside a register anyway. So let's cut all this out. I guess it's the C string name. And then, it's kind of like, yeah, it's basically like these. These ones, these floats, we're just giving it back as a memory address. So I want to do exactly the same thing from a C string. It's just a pointer, that's it, right? So it's just a memory address of this C string. Does that work? No, it does not. Maybe it's because it looks like we're the thing, like this is the pointer and this is the dereferenced pointer. So I guess actually what we want to do is return an immediate. But why don't we return an immediate for these? I'm not sure about this. But that seems happy now. See, look, it's one line now. One line. And here we're declaring a string. So let's just check that it actually did work, because we didn't actually print out a C string. So the C string is like this. And now we can see like error core F. Yeah. Okay, so it seems to be doing the C string stuff fine. Now what I also want to do is the same thing for strings. So at the moment we're allocating some space on the stack and we're copying the length and the pointer to the data into it. But what I realized is what we can actually do, if we find our data section here, here's our string in the data section. What I want to do is I want to say the string itself is the data, right? And then we can also make a data length, which we're making a 64-bit integer. And I believe it's equation $ minus this. Index, I think we don't need final string. Let's see. I think we need the DQ there to know that it's 64-bit. But this here, I think the $ is the address of this, of the thing we're currently defining, minus the address of this. So that should give the length of this. That's the idea. And then here, the actual string is going to be, what is it? It's the length followed by the data. So that's just going to be like index, index, index. I'm not sure that this is right, but let's see. And then, so then basically this is pointing to an object, which is our string object. You know, our string object is a length, 64-bit length, followed by a pointer. So this should evaluate to this pointer. This should evaluate to this length. I find that a bit weird, like wouldn't this be a pointer to this length? But apparently it evaluates just to the number. Let's see. So then that would mean that this also can look like this. You know, it's the same thing. Runtime assertion, that's fantastic. So we're trying to copy a string. From an immediate. You know, I think the string needs to be memory. I mean, I don't know why this is not memory. I find that really weird. Comma expected after operand 1531 in tests. This is probably where we're defining our strings. Maybe we don't need the DQ. I have a feeling, yeah. Let's take that away. Hey, there we go. A triangle. And if we go like this is a C string, but because we put the error in, when we go to compile shader, it'll print this out, which is a string. I think so at the end, yeah, it should say assertion failed to compile. So that's this assert here, which is printing out strings. So the strings seem to be working. I'm really confused about why does this one want to be an immediate? I don't really get that. Maybe because it's a pointer itself. I don't know, but so are these. I don't know. Anyway, that seems to work, and that's reduced our code, which I like. I like less code. So if we go to like our assert, here's assert. So we're copying our string. I'm sure that's less code than it was before. Okay, we have these 0 allocations that I'm noticing. So while I'm noticing that, let's take care of that because it's a super easy one. Just say if size is greater than 0, then allocate. Otherwise, what's the point? Very simple fix. For allocation and deallocation. Oh, we should fix up that error that we introduced. So yeah, we did see some 0 allocations here, but now we do not. Awesome. So I feel like we've taken care of that one. Only allocate if needed. Only copy stack address and expression if really needed. So that's another thing that's kind of annoying. Let's go to the top. Let's find an example. Here we go. So these two here, we're copying RSP into R10, and then we're just using it directly here. Like, why don't we just do this? Now that's really clear, right? We allocate some space, and then each of these lines is a parameter. There's 5 parameters. This here is aligning the stack for the call, and then that's undoing the alignment, and then there's return. So I think that's kind of what we want to go for. The reason for this is because sometimes we were doing allocations within expressions. One example was the strings were doing allocations. They're not anymore, so that's great. But still, the call can do an allocation. If we call a procedure as part of an expression, then the return value of that call is allocated on the stack. And it needs to stay on the stack until the end of the expression because it needs to be used by other parts of the expression. So basically, if an expression has a call in it, then essentially that means that it has an allocation. So I think we want to check whether that's true or not. Find out whether there is an allocation within the expression, and only then will we start doing this business. Otherwise, we'll just do this. Because I think a lot of cases, we can just remove this extra step and it'll clean things up. So I'll make a little utility, which is like, I never know where to put stuff now because we have so much stuff, so many procedures. Let's put it here. So let's say it contains allocations. Return a bool. So basically, if it's a call, and I guess for there to be an allocation, it needs to not be extern. So if it's a call and the directive is not extern, then we return true. And then for the children, so we're just going to, recurse. And we say if the child node contains an allocation, then we return true also. Oops, made things smaller. What's wrong with that? Oh, nothing's wrong with that. I think that's right if it's a call that's not extern, because extern calls do not do allocations. They just return in a register. I mean, later we might have to do some sort of allocations for extern, but right now we don't need to. So I think that's it. So we go back to up to our expression here, and we can say contains allocations. Node. And then I'm just going to pass that on. And that needs to get passed on to like all of these. Whoops. Oh dear. All of these procedures below also need to have contains allocations, And the primary also needs to know if it contains allocations. I think that's it. I think that's as far as we need to go. So we'll just fix up all these errors. Make sure it gets passed along. Oh, I put that in the wrong place. So where else? This is the left-hand side, actually, of an assignment, so that should never allocate. Okay, that's happy. And then here, contains allocations. Okay, so now what are we actually doing with that? Well, there's this copy stack address business, which happens for an identifier. That's the definition of it. It also happens, yeah, see for the return value of a call, it needs to do that. I don't think we'll get rid of that one right now, but we can get rid of this one up here. Where was it? Copy stack address. So let's say if contains allocations, else. So if it doesn't contain an allocation, we can just say, you know, we're getting it from the stack. So here's the stack address. We need to do this when there are allocations, because allocations change the stack pointer. So having something relative to the stack pointer doesn't really work. But this should work. Okay, we still have a triangle, that's good. Yeah, see, look at this. Real nice. Here's all our parameters. Why are they both RSP plus 8 though? Is that right? For create window? Oh yeah, because they're both the same variable. Yep, so that's right. Okay. Cool. Single allocation for calls. So we have an allocation here and an allocation here. I kind of wanted to streamline. And yeah, and like, look at this. Allocate, 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 allocate. Lots of allocations. So let's try and clean this up. So that's when we're generating a call. Where's our call? This is our call. Here. So what we do is we have this code that calculates the size. I'm actually going to move that up here. So if it's not extern, then we need to do this stuff, which will figure out the size. No, so for a call, I think a call node has the name node, and then it has parameter nodes. So I think we can just do param node in node.children, and then we'll just take a slice of it. So it's just, we skip the first one. Those are the parameter nodes. I think that's a bit cleaner. So that's the call stack size. And then also, I think I'm going to shift this up here. So if this plus the call stack size results in a misalignment, then I think at this point I'm just going to say misalignment equals misalignment 16 minus misalignment. And the reason I do that is because this modulo is going to give us, like, say this evaluated to 20, and we want it to be a multiple of 16. This is going to give us 4. That's the difference between the two, right? 16 and 20. But actually the misalignment we want is how far is it to the next 16, you know? So how from 20, the next multiple of 16 would be 32. So that's why we do this, to get that number. And so now we have this call stack size, which is like, that's how much we need to allocate for this call. Basically, we need to allocate enough for the return type, enough for the parameters, and enough to take care of alignment also. So then we don't need to do this in here. We just need to, yeah, this is just like preparing our parameters. Can we also just do like a nicer loop, like param node? Why don't we just do that? We do need a param index, but we can just go like that. I think that's nicer. We can take this out, and this misalignment code we've figured out. And really it's kind of like before we call the procedure, or is it up here even? Maybe we'll allocate the amount we decided we need to allocate. So we take out these allocations, but now we need to make sure that we're generating expressions for each parameter, and then we're putting them into the stack. But we can't just put them all at the top of the stack. We need to make sure we put them at the right place. And we've already allocated that space. Yeah, here we go. So we've already allocated like this space. We're doing the call now. We've allocated space for the alignment, the return, and the parameters. And the stack pointer is here now. So basically we want to go backwards from here to find out where we put these parameters and where we put this return. That's the idea. And that's going to be our offset, is how far back do we go. So I guess at the start we're at 0. Right? Or we could, because we have this here, this is kind of the so this here is the misalignment plus the return type size. So it's the size of this here. So if we start I guess call stack size. So if we go call stack size minus that, minus return only call stack size, what that's saying is the size of this minus the size of this. So that should get us to this point here, where we're, and is that what we want? Is that where we want to be? Yeah, that's the start of the parameters. Yeah, because we don't need to do anything for return. We just want to do for the parameters. So the first parameter should be here, right? I think that's right. I hope that's right. So we put it at that offset, and then I'm going to get the byte size of the parameter, and I'm going to reduce the offset by that much. So then when we come around again and do the next parameter, we're going to offset less of an offset from here. So we started here and then we subtract, so we go to there and we put that one in. I have a feeling this offset is not quite right, but let's see what happens. But again, we can do like, where is it? Here we go. Like this. So we don't really need that kind of stuff. Let's see. I think these offsets are probably actually wrong, but let's see what happens. Oh, we got a triangle. So this is where we were, right? And we had lots of allocations. So now we still have this one, which is, because it's a declaration, this is allocating space for the return value of the call. But this is actually allocating space for the call itself. Yeah, when I say it's the return value, this is actually allocating space for all of this stuff, but after we've finished the call and everything, the last thing that we need to do is this copy to copy it into the newly declared variable. So like if I go to the compile shader line here, that's copying it into this. We need to allocate this, which is not part of the expression, not part of the call. But that's what this allocation is. And then this allocation is for the call. And everything worked, so I assume that these offsets are all correct. So we do 3 copies, memory address to memory address copies. Because they're all variables, so they're all stored in memory addresses, and we're copying them to new places on the stack. So that's memory to memory, so that's good. It's a bit unfortunate that it's like 4 lines each, but this is as concise as we're going to get, I think. Unless we get a little bit smarter and sort of see, okay, based on the size, we could, well, a register's not even going to be that much less. So that's fine. Then after we've finished that, then there's this deallocation, which is deallocating just the parameters, which take up 484 bytes, so 16 bytes. So now this is the return. This is the other place where, actually I wonder if we can copy stack address. Maybe we can say copy stack address, be a bit more explicit. Yeah, so this is the copy stack address for the return value of the call. And then we're actually doing a deallocation, which is deallocating that return value. But because we kept a hold of this, we can then copy it to our newly declared variable. So it all makes sense to me, and I feel like it's pretty close to being as concise as it's going to get. I mean, you could combine these, but that's going to be a bit tricky. So I'm pretty happy, I think. And then this is a new declaration. This is a new statement. So let's keep having a look through, I think, and see, is there anything that stands out as not good? Or actually, no, let's have a look at the list, because I think single allocation for calls we've done. So this nil value is something I would like to do. I think the assembly is looking much nicer now. Let's have a quick look and see if anything stands out as like not looking nice. Got a nice little expression there. Okay, so you're taking a reference and then putting the reference into the parameter, so that's fine. I mean, I think it all looks pretty good. It looks much more concise than it did before. Much more readable. I'm quite happy. This is copying a float into a register, and it's using like a memory to memory. I wonder why that is. So I'm going to dereference. Yeah, I guess the dereference returns this as a memory address, and that's why it's doing this. I think that's okay. It's not so bad. Got some float stuff there, some float registers. Okay, I think I'm quite happy with this. So the next thing I want to do is this nil. So let's replace null pointer with nil. There is like this guy and this guy. So now we just have nil. Let's make it pretty so it stands out a bit. There we go. So we've got our nil in here. It's a bit annoying that we had to sort of maintain this point object as a null pointer. And so but nil is not just a null pointer. I want nil to mean 0. So you could assign it to anything. You could assign it to an array and it will zero out the whole array. Or you could assign it to a struct. We don't have structs yet, but it would zero out the whole struct if you assign nil to it. So nil is just like 0. So it's not a data type, but I'm just wondering how we change the grammar. I guess it's like goes in here. One of these, it's a primary. It's like a special primary. So I guess it's like the keyword nil can be a nil, or primary can be a nil. I think that's about it. I think that's the only thing it is. So in tokenization, I think I'm going to have like a special nil token, nil, and just because I think it's kind of an easy way to do it, I'm just going to do like this identifier stuff here. I'm just going to say, if it's if we find a nil, then just make it a null token. Same with if we find true or false, we make it a Boolean. Okay, so now we have a null token. Parsing, I don't think needs to change. Type checking. Well, actually, no, I think parsing does need to change because we have in the primary. Here we go, parse primary. So we need to have another case like this. So we need to say, if we find a nil, then we create a nil node. Like so. And if we go to primary here, wherever primary is. Here we go, type check primary. We also need to say, okay, if we find a nil, because I'm going to make it also a data type of nil. It's got its own data type. And by doing this, it means that it won't be valid to put it in expressions. Like I think you can't put like nil plus nil or nil plus 1. I mean, it wouldn't be the end of the world because it would just evaluate to 0. And so nil plus 1 would be 1. It's a little bit weird to allow that. I'm kind of, doesn't really bother me whether it's allowed or not, but we'll just leave it out for now. Okay, and here we go. Here's our immediate here. So if we come across a nil, that's just an immediate 0. That would be the location of the nil. It's just a 0. But we're not allowing it in expressions, binary expressions. Where's our expression code? See, we're not allowed to have arrays. We're not allowed to have a bool with these. But we don't restrict it to numerical types. I think it's either got to be a bool or a numerical type, and it can't be an array. I think it also can't be a reference, right? A reference couldn't be. Yeah, reference. We can't do a binary operation on a reference, so I'm just going to put that there. But now I think we actually need to put this as 2 ifs. So if it's a bool, yeah. So if it's like this, something I think I'm going to do. I'm going to change this in a lot of procedures now. I'm just going to do that. So that, because otherwise you end up just getting like lots of errors and it's not that helpful. And this invalid type business is they should be better error messages. But now it has to be either a bool. I guess we do need to do else if. Either needs to be a bool with one of those operators, or it needs to be a numerical type. So if it's not a bool and it's not a numerical type, then we have an error when it comes to binary operators. So we haven't included nil in here. So nil cannot be in a binary operation. Okay. I think we did this, didn't we? We made it an immediate 0. So another thing I want to do in generation is, I think we're going to have to go up a fair bit. Right, so we're up here. So this is where we copy, like when we're finished with the expression, we take whatever we've got. If it's a nil, this is going to be an immediate 0, and we put it in our destination. The problem is that if our destination is a memory address, that's not going to work so well. So I think we're going to say, and it can't be a binary operation, right? If there's nil, it's going to be just nil. If nil is an expression, it can only be just nil. So that would mean that this node's data type, or we can even say this node's type is nil. So if that's the case, and our destination type is memory, then we want to do something special. Otherwise, we can just do this, and it should be fine. Dest1 in this case should be the immediate 0 that we did before it below in the primary. And we do have, in our declaration, we have this 0 initialization code. So I'm going to copy that down. But I'm going to call it nil now. And the destination is this destination. And the size is the byte size of so this data type is going to be nil, isn't it? Well, maybe we can make it so that nil can be coerced to anything. I thought we had oh, this is type checking is where coercion happens. So like when we coerce our type, if we have a nil type, yeah, if our expected data type, like here, for example, our expected data type is a pointer to an I8, I think, but we have the type nil. So we need to be able to coerce. Let's do that a bit later. Probably we're going to get an error. But the other thing I wanted to do is put in here that, like, if we're dealing with nil, then I want to have a custom label for this copy, which is a nil copy. So let's try that. I think that's going to throw an error. Yeah, see, it's like saying that these are incompatible types. That's what I thought. So we need to probably look at our type coercion. So here we're saying if there's no type information, we just take the other type. So maybe we can do the same for nil. If it's a nil data type, then we just use whatever the other type is. We just automatically upgrade to the other type. Hey, that worked. That worked. Here we go. So we've got 2 nils here for creating window. Got another nil here for our buffer storage. All of them are just pointers, so they're just registers. So we haven't actually got any examples of doing a memory copy. Maybe we can try it though. If I say like, you know, blah is an I32 array, it's too long, and then I assign nil to it, it works, and it's like one of the first statements, isn't it? Here we go. Yeah. So it's allocated 8 bytes, and then it's done this nil thing here. Another thing actually that I thought of we could do is, you know, by default, if I do this, then it has this 0 business. 8 bytes? Oh yeah, 2 I32s is 8 bytes. Yeah. Yeah, the other thing I thought we could do maybe to simplify the code a little bit is, because we've got all this nil handling in the expression, maybe when it comes to declaration, we can just say that the right-hand side is a nil node. Does that work? So then that should change. This should be exactly the same. It should just say nil instead. Yeah, just says nil. But it has a count of 0. Why does it have a count of 0? What am I trying to look at here? This. Probably because it doesn't have the data type. They say the data type is also nil. No. But if we go in here, because this is generation, so basically how am I checking? Nil. Yes, the node data type, which is times by the length. So I was lazy and I didn't put the length in here, but it is needed. Oh, it's still not there. It's a nil node with a nil data type getting assigned to getting it assigned to that. So maybe that is an issue, like where the data type, I guess, actually needs to be whatever the left-hand side data type is. This guy here. There we go, 8. Bit of a mission. Okay, so now that's, I feel like that's a bit streamlined. Cool. So we're coming close to an hour, but there was one other kind of bonus thing that I wanted to try, which is this boundless. Should we try it? Let's give it a go. Let's give it a go. So we should be able to say like this, hash boundless. So when we're parsing a type, we have a parse type in here somewhere. Parse type. It could start with a directive. And if it does start with a directive, then we save it to, no, it's just to the node, isn't it? We put that directive on that node. Yeah. And I think we need to say well, if it's boundless, my idea is that we make it a length of 0 to signify that it's boundless. I mean, we have the directive as well, but it's nice to have it in the actual data type. So a length of 0 means that it's boundless. I kind of don't like the idea that we can put this square brackets at the end, because then that's kind of like saying something like this. Like, what's the point of specifying a size if it's boundless? Well, I guess that's okay. No, but this is a data type. This is a data type. I mean, if we did like this, actually, if we did like this, then it would just mean like, okay, we're allocating to, but just by the way, it's boundless. Okay, I think that's fine, actually. It's not required, but it's not a problem either. So we'll leave that there. So that's 0. So then I think the last thing really is, well, maybe not the last thing, but in type checking, here we go. When we're indexing, this is where we bounds check. We also set the length to 1 when we index. Oh, yeah, that's fine. That's fine. Data index. This is the length of the identifier node. So this is actually type checking a variable, which is, this is the variable. The data index. But it gets the data type from, yeah, it gets the data type from the actual list here. So this is the data type I think we're interested in. So if that length is not 0, i.e. it's not boundless, then we do the bounds check. And the last thing I can think of is we have this byte size of business here, which multiplies by the length. Actually, is that an issue? Like, if it's boundless. So boundless can only be applied to pointers, I just realized. Yeah, boundless, you could only have a boundless pointer. It doesn't make sense to have a boundless anything else, because, yeah, you can index a pointer. So the type, so this is what makes it a reference. So if it's a reference, if it's boundless and it's a reference, then we'll set it to 0. And if you try to make something else boundless, it's just going to ignore you at the moment. Probably should throw an error, but I can't be bothered with that. So it's only going to work for pointer types. And then when we're in here, because it's a reference, it's just going to say address size anyway. So the length doesn't matter here. Because I was thinking if the length is 0, it's going to evaluate to a 0 data byte size. So what happens there? GLU error string must have a procedure body. Interesting. Okay. Why? Because this boundless, because the return type is actually the type of the procedure node. So we've overridden extern with boundless. This is a bit hacky, but because we're kind of low on time, what I'm going to just do is say like boundless false, and then boundless true, and then I'll just say, you know, boundless and it's a reference. Yeah, so the only thing we save is a length of 0. That's the only thing that we save that could make it. Okay, so now we get incompatible types. So I think we need to say that like if this has a length of 0, then it's compatible with any length. And that's in type coercion. So here, so if that's not 0 and that's not 0 and they're different, then we have a problem. If either of them are 0, then it's fine. Okay. That worked. So when we go to our GLU error string, here's where we call it. We pass an error, which is from GL get error. Oh no, we return from GL error string the boundless thing, which we then pass into print B, and print B is expecting, I think it's expecting a certain length. So we should probably actually change that too. If we go to type checking for print B, I think it's a bit hacky. Yeah, it's got this 1 million, right? So if we change that to 0, then that's effectively saying that that's boundless. Because we have the length that we pass in afterwards. Cool. Okay. So I think what we can do now is change these to boundless. This is a boundless F32. I mean, ideally this would just be like return a pointer to some bytes, and then later we would convert it to whatever type we are dealing with. But at the moment, so that's another thing we could do, but at the moment we're just saying it's F32s. So yeah, that all works. Wow, I'm kind of surprised that we got boundless working. Let's go boundless so it looks nice. Okay. Cool. That feels less hacky to me. I like that we have nil and we have boundless. Yeah. It would be nice if instead of this we could get the correct length, because this will return the length of whatever info it put in, and then we could use that length here instead of 1 million to properly output the message. But the problem is this is expecting an I64, this returns an I32, and we don't have a way to convert yet. And I think we've done enough now. So we've got boundless. Wicked. You can see there's some other cleanup stuff that I want to do, but those were the main things I wanted to do. Just like a couple of things that stood out to me as annoying when I was doing the OpenGL code that we fixed up, boundless and nil. Oh, we don't need that anymore. And also the assembly was just getting out of hand, so the assembly feels so much nicer now. Next episode, I want to do this function pointer thing that I mentioned. We need to be able to pass functions around so that we could pass a function to a thread and do a thread. And then I have an idea of how I want to just like very easily take an array of data and a procedure and then use that to spread processing the array across a whole bunch of threads. If that makes sense. That's where I want to get to. So hopefully in the next couple of sessions we can do that. That'd be really awesome. But I'm pretty happy with what we got done today. Quite a lot of nice quality of life improvements, I think. Okay. So thanks for stopping by. Have a good one. Ciao for now.